What up, what up, what up? Physics lesson 8.3. Work. Alright, so let's see here. Let's get started. First thing we need to go over is being able to distinguish between types of forces. So there's two types that we deal with as far as energy goes. So we have a conservative force. This is pretty much anything that changes from potential energy into anything else. So this is not going to change. It's conserved. You put it in, it comes out, everything's set. Examples of this is gravity, elastic, electric, or chemical forces. Non-conservative force, this is basically any other type of force, and in here we're looking at an applied force. So Roy pushes Sally, Sally moves a book, Billy Bob lifts some kind of object. These are all going to be an applied force that is adding into the system and is not set. Work is looking at the change in energy. So whenever an object is moving, it's going to have a change in energy. The direction of the motion needs to be in the direction in which the force is applied. So if you apply something to left or right of an object, it needs to move left or right. If you are lifting something up, then the force that you are applying needs to go in the up direction in order for the object to move up. This means that you can have work that is negative. And for non-conservative forces, work is equal to the change in the total energy. Alright, so work done by all conservative forces and the object equals the change in the object's kinetic energy. So whenever we have a change in kinetic energy, so from rest to, 10 meters per second, we're having a change in kinetic energy, so we're having work that needs to be done. We got a quick example of that right here. Alright. How much work do you need to slow a 5 kilogram object, which is moving horizontally at a speed of 14 meters per second, to a new velocity of 6 meters per second? So what you want to do is figure out your change in kinetic energy, because that will equal the amount of work that you did. So kinetic energy to begin with, you should have had 1/2 your mass times your velocity squared. So your initial should equal 1/2 5 14 squared. I believe that is 405 change squared. Yeah, 490 joules. Work is measured in joules because it's a change in energy. That's what we started with. What we ended with for our final should equal 1/2 5 6 squared. So our kinetic energy here is now 90 joules. So just like we did with displacement, just like we did with change in velocity, it's always final minus initial equals our change. So 90 minus 490 equals a change of negative 400 joules. So the amount of work that is being done is negative 400 joules. Alright, so for a non-conservative force, we're looking at our change in our total energy. So again, final minus initial. Let's say we have Roy, and Roy is going to lift a box of papers from a desk. So let's say this is our desk. Here's our box of papers to a shelf that is taller. There we go. And there's our box. Now, how much work does he do? So initially, he had potential energy and kinetic energy. That should equal our total energy. So potential energy should be 5 times gravity times our height, 0.8, plus our kinetic energy. Well, that is 1/2 5 times our velocity squared. Well, sitting on a shelf, so our velocity is 0. So we have no kinetic energy. And our potential energy equals 40 joules. And that also equals our total energy. Yay for total energy. Our final energy over here still equals potential plus kinetic. Notice it's sitting on a shelf now, so our kinetic energy still going to be 0. Now it's 5 times 10 times 1.5. That's times, not a negative 1.5 times. And that should equal 75 joules. So final minus initial, we should end up with a positive work of 35 joules. Yes! I love it when things work out. Alright, more on work. So, in order to put energy into a system, you need to you need to do it with a force. Remember Newton's second law, force equals mass times acceleration. So in order for an object to change its direction, it needs to have a force applied to it. So work also equals the force that we are applying times the distance we are applying that force. But this only, again, works if our distance is in the direction of force. So when I say direction, I mean on the same plane. So if our object here, we're applying a force to move it upwards, then our direction needs to be in that direction upwards. We want to pull it to a stop, it would be going the other way, but it's still able to do so. Okie dokie artichoke. Let's try this. We have a cart. Let me draw my awesome cart. Doop, doop. Doop, doop. Doop, doop. Sound effects are needed to make an excellent cart. Alright, so here's our cart. It's a horrible looking cart. It looks like a trap from Ghostbusters. But anyways, whatever. We're going to deal with it. It has a mass of 40 kilograms. It's pushed from rest 12 meters across a horizontal floor with a force of 50 newtons. Find the final velocity of the cart. Alright, so work equals force times distance. So our force is 50 newtons times our distance, which is 12 meters, and we're not a room with space. So our work that is being done, our W, should be equal to 600 joules. But it's not asking for how much work did we do. It wants to know our final velocity. So that's going to come back into, well, work also, change the color, work also equals change in kinetic energy. So it started from rest, so we initially had 0 kinetic energy. So in this case, our work equals our final kinetic energy. So 600 joules should equal half of our mass, 40, times our velocity squared. And this will tell us how fast the cart is traveling. So 600 joules divided by 20, divided by 20. 30 equals v squared. That, square root that. And we should end up with a velocity of 5.5 meters per second. Alright, tune in next time. Same bat place, same bat channel, and we'll see if our elusive hero survives the night. Okay, goodbye.